All right. So, last time I talked about Voronoi diagram and then introduced Delaunay triangulation, discuss various properties of both of them. Today, I am going to talk about computing them. So, I will begin with Voronoi diagram and show an algorithm to compute them, and then I will say what it means in terms of Delaunay triangulation. Okay. So, let us begin. If you remember that you are given a set of points in 2D, and the definition of so that was the definition of Voronoi cell. Before I describe the algorithm, I need to introduce a concept, and what I will do is I will reduce computing the Voronoi diagram in 2D to computing the convex hull of a set of points in 3D, and that is what I will do. And then I will say, well, although you have not seen in the class, but you will see it later how you compute the convex hull of a set of points in 3D. And this reduction I will do works in any dimension, and that will also describe or explain what I said about the complexity of Voronoi diagrams in higher dimensions. Okay. So, the concept I need is what is called lower envelope. And I will talk about lower envelopes more next week. But suppose you are given a set of functions for our application. Let us assume each function is a bivariate function, but it can be again any number of variables you can have. It is hard for me to draw pictures in 3D. So, I will draw for univariate functions. So, let us say that this is a function f1, this is f2, let us say this is f3. Well, let me just keep only 3. Then the lower envelope, which I will denote as L of x, that is minimum, so what I am doing is I am taking the pointwise minimum of these functions. So, in particular in this example, what it means is that I just trace the lower boundary. So, this red curve that you see, that is a graph of the lower envelope, because I am studying the pointwise minimum. But what you notice is if you trace the lower envelope, then let us see if I can use this technology. Never mind. So, in the beginning left side you have f3 that is showing on the low envelope. So, here you have 3, then function 2 shows up on the envelope, then the function 1 shows on the lower envelope, then again 3, then 2, then 1, and so these are called breakpoints. So, if you trace the lower envelope, what is happening is one function is showing on the envelope, then there is you switch from one function to another function, then some other function shows on the envelope, and so on. So, what happens is that if you look at the, since I have drawn univariate function, what this low envelope does is it partitions the real axis or the x axis into intervals, so that the same function appears on the envelope within each interval. So, you have this is one interval, this is another interval, so you have the real axis is partitioned into intervals where the same function appears on the envelope. So, this partition of the real axis into these intervals, that is called minimization diagram. Okay. It will become clear in a minute what has this to do with the Voronoi diagrams. Thinking a little ahead, the way I define the lower envelope, one can also define what is called upper envelope of a set of functions. So, if I let me choose my another favorite color, that won't show, that is what I am thinking. Let us see, let me do green, I think this is fine. So, that is a pointwise maximum. I will not write it down. So, so lower envelope was pointwise minimum, you were tracing the lower envelope, and upper envelope is pointwise maximum of a set of functions. Okay. Now, why I need this? What I will do is I will define a function f I is a distance from x to p I. Okay. So, what does this function look like if you look at the graph of this function? Oh, I did not reach the minimization diagram yet. I am just asking you. So, if you look at the function f I x, what is the shape of this function? So, it is the Euclidean distance you are talking about. So, if I draw this function, what will it look like? No, do not go to Voronoi cell yet, it is a very much. So, function f I I have defined is for a given point x in the, let us say if this notion is confusing, think about as f I x y, and let us say p I is its coordinates are a I b I, then this is root x minus a I square plus y minus b I, right. That is the Euclidean distance, that is a distance function. Go ahead. Pardon? No, it is not a sphere. So, yeah, it is a cone, right, because sphere is a label set of this function. So, it is a circle. So, if I look at this function, that looks like, well, again, so let me try to draw. So, if this is point p I, that is how the function will look like, this cone. So, this is function f I. So, if you took the point any x, this value is f I x. Okay. Now, if I look at the lower envelope, so now you have these functions f I 1 for each point. Now, you get the set of functions f n. You did this for each point. Now, I look at the low envelope. So, this is minimum. So, what the low envelope means? What is this function L low envelope of these functions mean? So, remember the low envelope is pointwise minimum, am I right. So, when I look at these particular functions where f I is a distance from x to p I, then what is the lower envelope correspond to? It will be surface, but what does the point there mean?
So, it will be closer in the inside this closer to the p I.
Yes. So, it is a distance from x to the nearest point, am I right. So, this is the distance from x to the nearest point in S, and this is very related to Voronoi diagram. The way it is defined is the minimum point. Now, if I look at the minimization diagram, of f of this set of functions. Now, here I had done in this figure minimization diagram I had shown was for one dimensional function, for univariate functions. If I want to do it for 2D functions, bivariate functions, then so I just put it here and it will work. So, suppose this is your x y plane, and if you had a set of functions, you do the low envelope. Now, what you will get is you will get some partition of the plane into some regions, and here let us say f 1 is minimum, here f 2, f 3, f 4 and so on. In the different regions faces, the different function will appear on the envelope. Okay. So, it will be instead of a, when you talk about bivariate functions, instead of a partition of the line into intervals, what happens now is you have a partition of the plane into regions. Okay. So, that the same function appears on the envelope. All right. Now, can you guess what does the minimization diagram of this function will correspond to? So, if you look at a region, so within each region, same function f I appears on the envelope, am I right? Because that is the definition of the minimization diagram. That was the definition of minimization diagram. So, what does it mean is that if you look at the any region, it is the same function appears on the envelope, and in the case, in this particular case, a function appearing on the envelope, it means it is the nearest neighbor, and that is precisely the definition of the Voronoi cell. Okay. So, this basically it means that this region corresponds to the Voronoi of P I. So, if you take the minimization diagram and look at each region in this minimization diagram corresponds to the Voronoi cell of the point. So, minimization diagram of f, this is nothing but Voronoi diagram of S. So, what I have shown you is what the Voronoi diagram means is you define a set of functions, these are the distance functions, you look at the point where it is minimum and look at minimization diagram, which is nothing but take the functions and you project it on the plane, you get the diagram. So, one way of thinking about this is as follows. You draw these cones, this is one point, let me do it on the piece of paper. So, you draw these cones around each point. Well, I have drawn the finite cones, but these cones extend to infinity, and you look from below, you see some surface that is called Voronoi surface, you project it down on the plane, you get the Voronoi diagram. Okay. So, but so what? Okay. Yeah.
When you said that when you project, but the cone has this circular things, right? But when you project, it's getting a polygon.
Yes, because that is a very good question. If, and you will see in a minute, if you have a cone, if you take the two cones, these cones are identical. In general, that is not the case. If you take the two arbitrary cones, intersect them, it is not a, if you look at the intersection curve, project it, you will get a parabola, okay, or some conic. But in these special cones, these are two identical cones, they just shifted. Then you get the parabola you get of the intersection curve, then you project it, it will be a line which will be nothing but the perpendicular bisector of these 2 points of the apices. But you are asking a question, just keep it in mind. In next class, you will see the consequence of what you are asking the question. So, yeah, it looks sort of miracle, but that is what really happens, and you will see why, what is going on in a minute. Any questions about what I said so far? All right. So, it relates to this question. So, why this cones which are quadratic curves, quadratic surfaces, why does it lead to polygonal regions, convex, nice convex regions? And here is the reason. So, I define, let me start a new page. Let me define Gix is a square of quadratic of square of that function, which in this case, I remember there was a square root, I remove the square root. Okay. So, this becomes so, this is nothing but a paraboloid. I took the square. If you look at this equation, this function is a paraboloid. Now, what I am going to do is I am going to subtract the quadratic term. So, I define y square. So, what you get, the quadratic term disappears, thank you. Okay. So, I started with a cone. When I squared it, I got a paraboloid. When I removed the quadratic term, I got an equation of a plane. So, this is a linear function, this is a plane, and this was paraboloid. All right. So, what is all this good for? And here is the main claim. So, let H be this set of n planes, and here is the claim. Voronoi diagram of S, which we know is the lower envelope is the minimization So, what I am saying is that I started these functions f, and in the two stages I transformed them to function h. And during this transformation, the functions have changed, but the minimization diagram has not changed. Okay. Can someone guess? Can someone argue why this is the case? Why the minimization diagram has not changed during this transformation? Not constant, x square.
X and y, they don't vary for a single.
That is right. So, what I am doing is squaring does not affect anything, and I am subtracting a common term. So, it does not affect. So, let me just go through it. So, here is the proof. So, what I need to argue is that if for any x, if f I is less than f j, that implies that h I should be less than h j. If I can argue that, then minimization diagram will not change, because the relative ordering of functions has not changed at any point. So, what I need to prove is this implies that the same inequality should also be true for h I x and h j x. Well, I have this tendency of thinking of x as a vector instead of a scalar. So, let me just continue with that. So, this implies by the way, one thing I should say that f I and f j are non-negative functions, otherwise there will be trouble, little bit trouble. Okay, so, since they are non-negative, then this is the case, because squaring both sides does not change the inequality. You see that what the mess I am creating, because by maybe I should be careful and put a y also there to avoid confusion. I feel like a kid playing with a magic slate that I used to do as a kid. So, it is a f I square x y minus x square. Okay. And this is nothing but okay. because this was the definition of this was nothing but this is h I x y and this is S g x y. Okay. All right. So, what it means is that the minimization diagram of these cones is nothing but the minimization diagram of these planes. And let me show you geometrically what is happening. So, we started with these cones. Let me draw the picture in 1D because it is easier for me to draw. So, you had these cones. And this was the minimization diagram. I squared it, I replaced them by parabola. In that process, I did not change minimization diagram. In the third step, what I did was I subtracted minus x square minus y square term, in this one minus x square. So, what you think about is that you think about this horizontal line x axis as being a flexible bar. What you are doing is you are bending it downward. When you bending downward, this horizontal line is becoming a paraboloid or in this one dimensional parabola, and these parabola are stretching to a straight line. So, what happens is that this becomes like this, and the original parabola, they become lines in this one tangent to this parabola, and the same thing happens in high dimensions also. And the minimization diagram did not change in this process. But nice thing is that minimization diagram is now the minimization diagram of these lines in this one. And if I think about, so this is the set of points that lies below all the lines. So, it lies below each line. Okay. So, it is a set of points that lies below all the lines. If you think about half plane bounded by this line lying below this line, then this region is nothing but the intersection of these half planes, or in 3D it will half spaces. Okay. So, let me go now to the next page. So, if I define gamma I is so, it is basically the half space lying below the plane h I. So, here was your, let us say h I, then the region lying below it, that is a gamma I. Okay. Then the minimization diagram of the low envelope is the same as the intersection of gamma I, which is what I drew here, that the low envelope of these lines is nothing but the intersection of these half spaces. Now, you have learnt about intersection of half planes or half spaces. So, it is a, and if you take the intersection of half spaces, it is a convex polytope. And what you do is you take the intersection of these half spaces and you project it in the plane, and you get the Voronoi diagram. And I assume you have heard of duality, am I right? Okay. So, what it sort of says is that you wanted to compute the Voronoi diagram of a set of points, and what I reduced it to through this process, I reduced it to computing an intersection of n half spaces. Okay. So, computing Voronoi of is reduced to computing in 3D. Now, how do I compute the intersection of half spaces? I use the duality. Now, what I do is, just for some it will be easier to think about. I will reverse the z direction. Okay. So, if I reverse the z direction, in this 2D I reverse the y direction, then what happens? Earlier you were looking at the point was minimum, but if you look at it when I reverse the y direction, you are looking at the point was maximum. Am I right? So, if I define, so where was h I? Was h I was the equation was minus 2 I a x minus 2 b y plus a I square plus b square. Now, let me define h I bar x y is 2 a x plus 2 b y y square. Okay. So, this is I just took the negation of it. And now, if I apply the duality, then what the duality does is the following. Let me write so the becomes to a I to b I, that is what it maps to. And let now, what does the intersection of half spaces correspond to when you look at the dual? Convexal, right. So, now what happens is that you had this intersection of half spaces gamma I. I took these points, I dualized them, then dual of intersection of gamma I maps to convexal of H star. So, what I did was I started a set of points in 2D, I wanted to compute the Voronoi diagram. I mapped them to a planes in 3D, and I said Voronoi diagram is nothing but take the intersection of these half spaces and project them. Now, I did the use the duality. I mapped them to a set of points in 3D, and I am saying it is a dual of the intersection of these half spaces is nothing but the convex hull of these point sets. So, what I did was, if I put all the pieces together, the Voronoi diagram of a set of points in 2D maps to a convex hull of a set of points in 3D. Now, you will see later in the class that you can compute the convex hull of a set of points in 3D in n log n time. So, convex hull can be computed in log n time. So, what that implies is, for now let us assume this as a black box. What this implies is that you can compute the Voronoi diagram of a set of points in 2D in n log n time. Now, this everything I said so far except the last sentence, it works in d dimensions also, in high dimensions. So, the convex Voronoi diagram of a set of points in d dimensions maps to a convex hull of a set of points in d plus 1 dimensions. And there is a classical theorem in convexity that if you have a set of n points, and if you look at the convex hull of n points, its complexity is n to the power d over 2 floor. So, what is called, actually it is so called upper bound theorem. The number of faces on the convex Now, in our case, when you are looking at the Voronoi diagrams in d dimensions, it was a convex hull in d plus 1 dimensions. So, you take the d plus 1 over the floor, which is the same as d over 2 ceiling, and that is what I had said last time. Any questions?
So, here you are saying that suppose you have a d dimension convex Voronoi diagram, and that can be translated into a d plus 1 dimension convex hull.
Yes.
Generally, I mean, when you do your objective will always be to reduce the dimensionality, right, instead of increasing it.
So,
it's not shouldn't I take a d dimensional convex hull and compute?
No, well,
complexity, right?
Well, you could try, but it won't work. So, because what is the case is that Voronoi diagram, by definition, by Voronoi diagram, as I sort of what I showed you was that. So, that is why I went through this instead of the reason I went through this whole steps is to sort of not to give you as a mystery why that is the case, because what is the Voronoi diagram? Voronoi diagram is nothing but this minimization diagram, because it is inherently defined by the set of functions, and the set of functions sit in high dimensions, and you are taking their lower envelope and projecting them into d dimensions. So, Voronoi diagram involves a projection of a d plus 1 dimensional object to one lower dimension. That is how it is coming, and here it is a convex hull in one higher dimension. That is why it is in d plus 1 dimension. There is a generalization of Voronoi diagram, which I hope I will say it in one higher dimension, sorry, on Friday, what is called power diagram. Voronoi diagram is a very specific case of that, and that is inherently is d plus 1 dimensional object. It just happens to be a specific case. For example, the way another way of thinking about is the following, that the Voronoi diagram is a lower envelope of these planes which were tangent to this paraboloid. Now, in general, if I draw some planes, they will not be tangent to paraboloid. One can talk about taking some arbitrary planes and take the lower envelope, and it will reduce to some generalization of Voronoi diagram, and that will be d plus 1 dimensional object, and this just happens to be a special case. Now, here I did the duality, am I right? Because where did I do it? I use a duality here. I took this, I had the set of half planes, I dualized them to set of points. In the last class, I talked about the duality in the planar graph sense. I said Voronoi diagram and its a dual was Delaunay triangulation. So, now what is the relationship between this convex hull? What will this convex hull look like if you take this convex hull, right? So, I am doing a duality here, right, because here is I am saying the dual of this intersection is a convex hull, but I had this convex hull in one higher dimensions of the set H star, okay, and I take the convex hull. So, what I if I want to go back to Voronoi diagram, what I do is I have this set of points H star, I compute this convex hull, map it back the dual, I get the intersection of these half spaces, and then I project it down, I get the Voronoi diagram. But if I take the convex hull and I project the convex hull back down to 2 dimensions, because H star is a set of points in 3D. So, convex is a 3D convex hull. If I project it down to the plane, this convex hull, what will I get? I will get the Delaunay triangulation of the point set. And to see that, you have to be a little careful, because
but I have a question here. I mean,
yeah,
dual here you are giving the transformation here, and here when the dual you are talking about in the plane Voronoi to Delaunay, that's a planar dual. So, are they equivalent?
So, in general they are not, but this is a magic in this case. It just works out like magic in this case. But in general, you are right, it does not all work like this. So, this is a general theory, and I am just not showing the whole theory, I am just showing you some kind of a special case of that, and that is why it looks like magic. And I will not have time to really go through the whole stuff and to talk about it when this is really works. So, if you remember that, so H I was 2 A I 2 B I A I plus by square. What I do is I scale it by a factor of 2. So, let us define the set of points, let us call it H I sharp. I divide each coordinate by a factor of 2. So, I just shrink everything by a factor of 2. So, then what happens? It becomes A I B I and notice that A I B I is similar to the coordinates of the ith point. So, what happened? So, if I look at the, so if I define H, oops, and remember that what was set S? S was, to remind you, was A I B I. So, if you look at the set S and H sharp, the x and y coordinates are the same. S was a set of points in 2D and H sharp is a set of points in 3D, but the x y coordinates are the same, but they have only z coordinate. So, how do you get H sharp from S? So, this is a lifting transform that you have seen in the class, I believe.
Is it like a parabola?
Yes,
taking it from the
precisely. So, what you are doing is the following. Again, I will draw only in one dimension. So, I will write the equation in general in 3D. It's 2, and if you had the point P I, you just lift it to the parabola. So, if you want to compute a Delaunay triangulation, here is the one way of doing it. Take the set of points, lift them on the paraboloid, z is equal to x square plus y square over 2, take its convex hull, project it down, you get the Delaunay triangulation. So, there is a deep relationship between Voronoi diagrams, convex hulls, Delaunay triangulation and convex hulls, they are all related concepts, but you just have to think in one higher dimension. Any questions?
So how do we know that this gives a Delaunay triangulation?
Good question. I will answer your question in a minute. Any other questions of what I said so far? I will before I answer her question. So, why is this convex hull is a Delaunay triangulation? I will not give you the complete proof, but I will give you partial proof and then you can fill in the details. Remember what I said for Delaunay triangulation. Delaunay triangulation had the following property: if you took this was a triangle PQR, if it was a triangle, if you take the circumcircle, this does not contain any point, all the points lie outside this circumcircle, am I right? So, that was a property. And let us now talk about what does this correspond to in 3D. So, what I did was I took the set of points in 2D, I mapped them on this paraboloid. Okay. So, ignore the so if you have a circle, let us say circle C, whose center is let us say alpha I beta I, this is center and this is the r I is the radius. Okay. So, center in the so you have circle in 2D and this is r I. So, the equation of the circle is I assume this you have seen, might have seen this one. Okay. And the points lie inside the circle that correspond to if the point x y lies inside circle, you replace equality by less than equal to. If it is lies outside, it becomes greater than equal to. Okay. So, now if I open it, and if I replace this one with the equation z, then what you get is you can write it okay. So, what happens is that I took the equation of a circle, I mapped it to a plane in 3D. So, a circle becomes a plane in the in 3D, and this is a general techniques in algebra that is used a lot. This is called the linearization technique, and it comes in many different areas. That number of times it is hard to deal with the higher degree terms variables, and if you convert if you have a function which is is not nonlinear function polynomial, you can map it to a linear function in higher dimensions, and that is what is going on here. So, you are dealing with the cones or circles and you are mapping it to planes in one higher dimension. Okay. So, that is what I did. I took this circle and map it to it becomes a plane. And if you look at what I did was the transformation was x and y did not change, but x square plus y square became z. So, this transformation, lifting transform, this is called a point x y is being mapped to x y x square plus y square. Which is very like there is a factor of 2 issue here, but it is very similar. This is very similar to what was going on earlier, right? A I b I a square plus b a square 2. This similar. So, I am again taking a set of points and mapping it to paraboloid, and the circle now becomes maps to a plane. Then what really happens is, if you look at the convex hull and of these points that are sitting on this if you take the convex hull, which in 2D it is a polygonal chain, but what happens in 3D you will get something like triangles, and it will be a I am not good in drawing these shapes, but it will be, think about your set of points on the paraboloid, you will get some triangles and you will get some convex polytope. Now, if you take the plane containing one of the triangles, what this happens if you take this plane, if you project it, take this intersection with this paraboloid plane and intersect with the point, when you map it down you get a circle back, and a point lying above the plane means point lying outside the circle in the plane. So, if you remember that the condition for the Delaunay triangulation was that all the points should lie outside the circle, and what it sort of means here is that all the points lie above the plane, and that is the case because of convex hull. If you take any triangle of the convex hull and you look at the extent to the plane, that all the points lie above it, none of the points lie below it, because since it is a plane defining the supporting the convex hull. So, what it means is that when you project it back, so the planes are mapping corresponding to the circles and all the points lie outside the circle, and which is means it is a Delaunay triangulation. Okay. Now, I see that I have about, how much time do I have? Few minutes, or I am out of time? Couple of minutes. So, how do I construct a convex hull of a point set? And let me describe in 2D, and then you can imagine how it happens in 3D. So, think about the special case when all the points are in convex position, right? Because if a point lie on a paraboloid, on the parabola, all the points will be vertices of the convex hull. So, then what you do is, you suppose you have computed the convex hull of some points. So, think about in 2D you have computed some point. Now, I am adding a new point, let us say. Then what you do is, you think about, you compute this tangent in 2D, and you are going to remove this portion and replace it by this portion. That is what happens. Now, the way you think about, the way one way of thinking about, physical way of thinking about is, you have a convex hull which is a convex polytope in 3D. New point, think about the light source. Whatever it can see, when you put the light, some part of the polytope is being seen, some part is not seen. The portion that is being seen, you remove it, you get a hole which is a silhouette. Take each silhouette as an edge, take this edge, connect to the point, you get the new set of points. In 2D that is what is happening, you have this edges that you can see, you remove them. In this case, silhouette is only consists of 2 points, you connect them by segments. But in the 3D, the silhouette will look like some convex polygon, and here is your point, and you are going to this one. Now, what does this correspond to? Now, I said this convex hull is nothing but, if you project in the plane, it is nothing but Delaunay triangulation. Then one can ask, do I really have to go through all this mapping, or I can think directly in terms of Delaunay triangulation? What is going when you insert a point, what really goes on? And in the next class, I will tell you what it means directly in Delaunay triangulation. Okay, so I will stop here.